All right, everyone. So there is homework due on Friday, but there is no quiz on Friday. But instead, we're going to have the practice exam in class. So I'm going to hand it out. You can take it, ask questions as if you would in a normal exam, but it should be a sort of a benchmark to know sort of your proficiency level at the time. Yes? It's not like it's graded. No, not graded. This is for fun. Okay? Yes? Yes. The solutions will be released. I won't go over them, but I think if you go through the videos from last year, usually when I hand back the exam, sometimes I'll go over the questions. I don't remember if I did last year, but I'll post the solutions, and then I'll also kind of talk through like my approach. I mean, I don't remember if I did it last year, but there may be me actually talking through the solutions in the videos the day after the exam is returned, which is usually the Friday after it's taken. So you have a 1-week turnaround. I'll check the video, and I'll let you know on Friday to see if I give those there.
Because the Friday after is the test, yes?
I mean the Friday after the date that the test is usually on, which would be like 2 Fridays from tomorrow, is where the video may exist where I actually go through the solutions.
Okay.
And I'm trying to be as confusing as possible. Okay, so today we're going to talk about equations of state, because we're now in our thermodynamics section. So now that we know how to figure out how much mass is entering and exiting, now we can start to manipulate more physical properties, right? What is the density at a given temperature and pressure? What is the volume that the tank needs to be given the density of the fluid and things like that, right? So this is the material properties that help us actually start to design and control the variables in a real way that actual engineers would do. So an equation of state relates between these 3 variables: pressure, temperature, and density or specific volume. In some thermodynamic circles, this is density, but usually in the equation of state, it's set up as the specific volume. And recall that the density is just the reciprocal of the specific volume. If this is mass density, this would be the specific volume with respect to mass. If this is molar density, this would be the specific volume with respect to moles. Right? The nomenclature may vary from discipline to discipline. For the purposes of this class, really what we're trying to do is figure out densities. But in actual thermodynamic application, the equations that we're going to talk about are actually used to relate between internal energy, entropy, and specific volume. People really hate thermodynamics, but it is a brilliant field of study because we have taken these concepts that are very confusing. Internal energy, what is that? Entropy, what is that, right? And recall these terms were developed before we knew that atoms and molecules existed. But the system works really well, so no one wants to change it. The power of thermodynamics is that for any single component system, I need only define 2 of these variables to calculate the third. Which means that if I have any 2 thermodynamic variables, I can calculate all the others. So if I were to give you temperature and pressure, you could calculate what the entropy of the system was. If I gave you temperature and pressure, you could calculate what the density of the system is. If I gave you temperature and pressure, you could calculate what the internal energy is. Phase equilibrium occurs when the Gibbs free energies of the liquid are equal to the Gibbs free energies of the vapor. This is what you'll talk about in Thermo 2, but I'm giving you a brief preview. The Gibbs free energy is the enthalpy minus TS. So the enthalpy of the liquid, the entropy of the liquid, enthalpy of the vapor, entropy of the vapor, right? So this is the Gibbs free energy. All of these are thermodynamic state functions, which means that if I have an equation of state that can predict what is the density of the fluid at a given temperature and pressure, I can actually calculate when it will boil, what its phase transition is going to be, what its density is going to be. Right? So the equations of state that we're going to talk about were not developed to just calculate the density. They use the density to optimize the equation so that they can calculate these properties. These equations of state were developed largely in like the 1970s, and up until this date, they're still being developed. They were largely made by oil and gas companies to figure out how to optimize distillation columns and how to optimize for reservoir flow simulations. So in an oil reservoir, you punch a big hole into the ground, right? It could be a mile or so deep. These reservoirs can be several cubic kilometers, and at every point in space in that reservoir, you want to know what is the density of the fluid, is it a vapor, is it a liquid, can you predict its viscosity, what is its pressure? And then you simulate how does that pressure cause everything to flow, how much oil should you expect, right? And so you need to solve these equations millions and millions of times in a simulation because you make a little box of rock, and that's one voxel. And within that voxel, there's a certain temperature and pressure. You need to know what the phase is, what are the transport properties, how quickly is it going to flow, right? So the equations of state that we're going to talk about, we're going to focus on this area over here, but just note that they have much more utility in generalized thermodynamic calculations. Okay, so we've been over this. What is the equation of state that we all know? PV equals nRT. So we're going to start off with the ideal gas law. PV equals nRT, or PV equals RT, or P equals rho RT, or P equals rho KBT. These are all different forms of the ideal gas law. Pressure, pascals. Volume, cubic meters. What units is a pascal cubic meter? That's a joule. N is moles. T is in temperature, usually Kelvin. R, 8.314 joules per mole Kelvin. 8.314 meters cubed Pascal per mole Kelvin. So this is energy equals energy, right? Right? So there's a lot more contained in these equations of state. Here, I just substituted N over V, which is the specific volume, volume per mole. This one here, I just moved it to the other side. So this would be molar density, right? Moles per volume. What's this one here? What did I do tricky on this one? Who knows what the Boltzmann constant? Who's heard of the Boltzmann constant? Does anyone know what the Boltzmann constant is? KB. What's the relationship between R and the Boltzmann constant? They actually communicate exactly the same information. And I feel like no one tells you what R actually means. Does anyone know what R means? All right? Okay, joules per mole Kelvin. I'm going to give you the units of the Boltzmann constant. What's the difference between the Boltzmann constant and R? Well, it's so the Boltzmann constant is the ideal gas constant, not per mole, but per molecule. So it's a very small number, times 10 to the minus 23, because Avogadro's number is a very big number, 6.022 times 10 to the 23. So if you take 8 divided by 6 times 10 to the 23, you get the Boltzmann constant. Yes?
Sorry, so it's joules per mole on the top?
Joules per mole Kelvin. Boltzmann constant is joules per Kelvin. What does the ideal gas constant mean? And conversely, what does the Boltzmann constant mean? Yes?
So is the Boltzmann constant kind of like help you find the energy per molecule?
Very close, yes. Of what kind of energy? Not entropy. Kinetic energy. Who said kinetic? Nailed it. Temperature is a construct, right? Temperature isn't involved in the fundamentals of thermodynamics. We didn't know what temperature meant until Boltzmann and Maxwell developed the kinetic theory of gases. This was the first true evidence that atomic theory was correct, and it didn't come into being until the 1890s. People didn't believe it was true until the early 1900s when Einstein demonstrated that Brownian motion was caused by atoms. Right? So the first real evidence that atoms existed came from Brownian motion, Einstein, and Boltzmann. The reason why no one believed it was true is because Boltzmann constant was very, 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 very small. The Boltzmann constant and the ideal gas constant are a proportionality relationship between the kinetic energy of a particle and its temperature, right? So it's easier to see here, energy per temperature. This is the kinetic energy of a mole of material, or the kinetic energy of a single particle. So the gas constant is effectively the consequence of how we define temperature. So in order for all of our equations to work out, this is what the constant has to be to translate between our definition of temperature and the kinetic energy of particles. Okay. That's a little bit of a sidetrack, not critical to know, but I feel like it's interesting because how many times have you guys used the gas constant? All the time. Has anyone ever told you what it means? Well, that's a shame, right? Okay. Ideal gas law. Under what circumstances is the ideal gas law applicable?
Under ideal circumstances.
Well, that's very helpful. Okay, so under what assumptions, because the ideal gas law can work, right? Obviously, Boyle and some other chemists from the 1800s sussed it out. Yes?
Isn't it at low temperature and pressure?
It is at low pressure. What is the property of a fluid? What's the density of a fluid at low pressure?
Incompressible.
Not quite. Does it have a high density? So if I squeeze something, does that increase the density? If I expand something, does that decrease the density? So low pressure, low density, or high specific volume. And instead of low temperature, if I increase the temperature of something and it expands, that also lowers its density, right? So this also applies at high temperature. Right, this is when the ideal gas law is good. What are the assumptions that go into formulating the ideal gas law? Yes?
Is it that each particle is infinitesimally small and that they have no interaction between each other?
Those are the two main ones, yes. So the assumptions are no interactions, and that there are, we could say infinitely small. Yeah, we could say infinitely small. That works just as well. And what this basically means is that there's no region in the container that a gas molecule cannot go. If we were gas molecules sitting in this classroom, would we be ideal gases? Can I go sit in any arbitrary chair? No. Some of you are in those chairs, right? If I can't go to a particular location, I am no longer an ideal gas. The concept contained within there is called excluded volume. There is some volume of the container, V, that I can't go to, right? So the ideal gas law assumes that there are no interactions between particles, right? Basically means that I would be in this room by myself. That would be the assumption that we are taking in an ideal gas. Now, as a liquid, obviously that's not going to be the case because liquids are very crowded and very dense. But as a gas, these assumptions are true when there's so few particles that when they bump into each other, it doesn't really matter all that much, right? The ideal gas law is not good for the purposes of a lot of the calculations we want to do as chemical engineers. It doesn't predict the existence of liquids. It took until, I believe, 1870 for van der Waals to develop the van der Waals equation of state. And if anyone is interested in going to graduate school, Mr. van der Waal earned the Nobel Prize in physics for his PhD dissertation in the development of the van der Waals equation of state. So we'll talk about that in a little bit. We can still do a lot of interesting calculations with the ideal gas law by invoking a material balance. So if I say N is equal to PV over RT, I can say that N1 is equal to N2. It's a material balance. So if this is a closed system and I'm not changing the number of moles, then I can say P1 V1 over RT1 is equal to P2 V2 over RT2. So by linking the equation of state with the material balance, right, this is my material balance, N equals out or initial equals final, I can then relate, if I change some state variables, I can figure out how the system is modified, right? If the volume is constant, that means R and V would cancel out. If the temperature is constant, that means R and T would cancel out, right? So we can manipulate this in a lot of different ways. So I got one more definition that's sort of based on the ideal gas law, and that's the concept of partial pressure. Then we'll talk about more advanced forms of equations of state. So the pressure we can model as summing up all the partial pressures. So the partial pressure is effectively the pressure that is exerted on the surroundings as a result of only molecules of type I. This only works in actuality for an ideal gas, because in a real fluid and there's interactions, it's kind of everyone's fault for the pressure being the way that it is, right? So if you mix two molecules that like each other, right, you'll have a system pressure that gets lowered because they're more attracted to one another and they won't push on the wall as hard, right? But in an ideal gas, the partial pressure is a very useful concept. So then we can write that the partial pressure times the volume is equal to the number of moles of just species I over times RT, I mean. And so we can know that the mole fraction is equal to the partial pressure over the system pressure, right? Which is equal to the number of moles species I over the total number of moles in the system. And so partial pressure is a useful concept. It comes up a lot. And the reason why it's going to come up a decent amount in this class is because the partial pressure of species I is going to be equal to its vapor pressure at some temperature in humidity and saturation. Humidity. All right, so this is going to be something that's useful for us to figure out like how much water is in the air on a given temperature day. If you have a volatile organic compound, how much is going to evaporate in the vapor space of a tank. And the example I gave the other day was to how much vapors are being released when you fill up your car with gas. Okay, so let's talk about more advanced forms of equations of state. So I'm going to talk about, let's talk about general phase properties first of all. So I'm going to talk about a phase diagram here. Because in order to understand the equations of state, we have to understand a little bit about the properties of matter. So I'm going to draw a PT phase diagram, meaning pressure, temperature, right? We can draw a lot of different phase diagrams. We can draw a density temperature diagram. We can draw a pressure volume diagram, right? There's lots of different ways to look at this. But basically, if I fix my pressure and I fix my temperature, that locks me into one point in space. That goes back to our principles here in an equation of state. If I lock in one state, I know everything about the system. Right? So we're going to see a lot of engineering charts and diagrams, but they all follow the same principle. Lock two things in, and you can read all the properties off. So in a phase diagram, it's going to look a little something like this. Okay? At low temperatures and high pressures, we're going to be a solid. So like ice has a certain freezing temperature. So if this is room temperature, or if this is atmospheric pressure, this would be at 0 degrees Celsius, right? 1 atmosphere, 0 degrees Celsius, water will freeze. If I'm at low pressures and high temperatures, I'm going to be in the vapor state. So in the case of water, this point right here, actually at 25 degrees C, let's say 25 degrees C, this point right here is approximately 3 kilopascals or 0.03 atmospheres. All right, so if I'm at if I'm at room temperature and I lower the pressure of the system, I can cause my water to boil at its vapor pressure. So in this condition here, I'm going to be the liquid. So if I follow along at 1 atmosphere pressure, I should expect to boil at 100 degrees C. In Salt Lake, it's a little bit lower because we're not at full atmospheric pressure. What is this point right here? This point right here. So this line stops. This is called the critical point. And above the critical point here, we call this a supercritical fluid.
Does that mean that temperature of the material or substance can't change anymore past that point?
So I'll show a video actually of the critical point in a moment, but the critical point basically means there can be no more liquid vapor transition. So what ends up happening as I move along this curve, right? This curve right here, this represents the vapor pressure of the system. As I heat up along this curve, so I have vapor and liquid in coexistence at all times, what ends up happening is I'm heating up and I'm also increasing the pressure. Because of the temperature increase, my liquid is going to expand. Because of the pressure increase, the density of my liquid is going to shrink. And eventually, the properties of the liquid and the properties of the vapor will meet, and they'll be indistinguishable. So then above this point, I can no longer have a vapor-liquid phase transition. The interesting thing, though, is that we base all of our thermodynamics on a concept called corresponding states. What the principle of corresponding states means is that all fluids behave the same with respect to their reduced properties. And what I mean by that is temperature reduced is the temperature divided by that fluid's critical temperature, and the reduced pressure, which is the pressure divided by the system's critical pressure. So a fluid like water is a liquid at room temperature and pressure. Its critical point is around 600 degrees Celsius. So at room temperature, its reduced parameters are very, very low. So at this point here, this would be TR equals 1, and this point here would be PR equals 1. So in the case of water, at some reduced temperature that's low and some reduced pressure that's low, that's why water falls in the liquid state. Now something like argon, right, has a critical temperature around 100 degrees Kelvin, so minus 200 degrees Celsius. So argon at room temperature and pressure is way above its reduced temperature, its critical temperature and critical pressure. So argon is then going to be in the supercritical regime. That makes sense? Nitrogen has a very low critical point. That's why it's a gas. Oxygen has a very low critical point. That's why it's a gas. But if I were to plot this phase diagram for water, for nitrogen, for argon, for neon, right, for methane, for propane, for gasoline, for everything, they would have very similar shaped phase diagrams, but instead of plotting the temperature, we would plot the reduced temperature. Right? So the principle of corresponding states allows us to take all the complexity of the universe and simplify it down to one measurement, the critical point. That is the basis for all of these equations of state that we'll talk about. Yes?
But it kind of seems like we won't often deal with stuff in, like, past the critical point. Is that right?
Yep. For a lot of fluids, yes. So on this phase diagram, where is the ideal gas law going to be accurate? Is it here in the solid and liquid regime? No. It's going to be accurate sort of in this area here. Ideal gas law. We would like an equation of state that could predict absolutely everything. Turns out that's very hard. But we can get an equation of state that sort of gets this area pretty well. Right? We would like to model this liquid vapor transition, particularly for chemical engineers. That's what we really care about. So I'll show you a video of the critical points at the end of class, and I'll talk a little bit more. But basically, we're going to talk about 3 different ways, and then I'm going to put some equations on the screen because they're kind of really cumbersome to draw out. But we're going to talk about 3 different ways that we can improve the ideal gas law. Okay, so the first one is going to be using generalized compressibility charts. Okay? And the way that I like to think of this is sort of like a times or divide correction. And the basis of this is something called the compressibility factor. Z is equal to PV over RT. Notice this is a V under bar. So if I were to take my ideal gas law that has the same form, PV equals RT, and I were to move RT to this side of the equation, for the ideal gas law, what would Z be equal to? So I go over here, I move PV over RT. This has to be equal to 1. Right? So an ideal gas has a compressibility factor of 1. For a non-ideal gas, I call this sort of a times and divide correction, right? Because we're multiplying or dividing this by a certain amount. So we could also write PV equals ZnRT, right? All I did is broke apart the V into V and N, right? So PV equals ZnRT. So this is saying, actually, the pressure is a little higher than we'd expect for the ideal gas law. That would be the case for Z greater than 1. Oh, actually, the pressure is a little lower than we'd expect for an ideal gas. That means Z is less than 1. Yes?
Are we saying Z is a function of the reduced pressure and reduced temperature?
Correct. And I'm going to show you those charts in just a minute, but I'm trying to lump all of the computer-aided stuff towards the end. Okay? So this is one strategy, and we'll talk about that in greater depth. The second one here is the virial equation of state. And this one I like to think of as a plus-minus correction. Again, I'm going to put it on the board. The resource that I have is going to cover it in more detail. And then the last one here, 3, is the cubic equation of state. And this corrects the assumptions of the ideal gas law. Okay, I'm not going to write out these equations. They're very big and long. So I'd rather just display them on the screen, and then we'll talk through some more details about that. So let me just get that queued up here. And this is the wonderful benefits of coming to class as opposed to watching the videos. But for those of you watching at home, this chart, this is in the resources for the Canvas page. Make big, there we go. Okay, oh, it's not on. Display to on. Okay, so let's talk some more about these equations of state. So I have here the virial equation of state. This one was developed in maybe about the 1920s. This is based on statistical mechanics, right? So statistical mechanics is a field of study that is sort of in advanced thermodynamics. And it was developed in order to get our existing thermodynamics that had worked really well for hundreds of years to agree with the atomic theory that had been posed by Maxwell and Boltzmann and validated by experimental measurements. So then the world knew that everything was actually made up of atoms, right? So statistical mechanics is a graduate level, or in your physical chemistry class, right? In chemistry, if you take that, they'll cover a little bit of statistical mechanics as well for the kinetic theory of gases. But the virial equation of state basically says, you know what? Let's assume particles actually interact. And it's a very complicated derivation, but ultimately you'll see that it has a lot of similarities to the ideal gas law, right? Z is equal to PV over RT, which is 1, so that's the ideal gas part, right? Z equal to 1, plus a few corrections. Now this B of T term here is a function of the critical point, right? So we're assuming that all fluids have similar properties with respect to their critical point, and it has a couple of additional correction factors, right? This B naught is a function of the reduced temperature and some coefficients. This B1 is a function of the reduced temperature with some other things, right? So it looks big and complicated, but if you put this into a computer, you put this into an Excel spreadsheet, break it up into small steps, and it's really quite trivial, right? The complicating factor is this results in actually a quadratic equation. So there's 2 roots. One of them is stable, one of them is unstable, and it's usually pretty obvious which is the right one, right? It should be the one that's kind of close to the ideal gas, right? Virial equation of state works reasonably well if you're close to ideal gas behavior. I'll talk one more in a moment about this omega term. Actually, let me just talk about omega right now. Omega is in a thing called the eccentric factor. Okay, so the eccentric factor is an explicit equation Don't worry about this. You can just look up what the eccentric factor is. People have calculated it for you already. Effectively, the eccentric factor is a small correction to the principles of corresponding states. So what the eccentric factor does at a reduced pressure, at TR equals 0.7. So what this means is that at a TR of 0.7, it basically corrects this curve to meet some point right there. So it's a small little tweak that we add in to this principle of corresponding states. It's often described as how spherical a molecule is because the eccentric factor was derived based on the noble gases, which are spherical compounds. Right? So their eccentric factors are 1 at this condition perfectly. And so then if it deviates from 1, that means it's not as spherical. Right? But it's not quite as clear as that. So I have an example here. The eccentric factor for carbon disulfide is 1.09, right? This is a linear molecule. It's got 2 double bonds. It's got a straight structure, right? So obviously not spherical, right? Okay, so its eccentric factor deviates from 1. So for example, argon, its eccentric factor is 1. But I have an example here, carbon dioxide. Its eccentric factor is 0.239. Okay, so can someone tell me the difference between this molecule shape and this molecule shape? It's the same, but they have completely different eccentric factors. So I never liked the description that it's a measure of the spherical of the molecule. It's just another fudge parameter. Okay. So the eccentric factor, type into Google, eccentric factor of water, you're going to get a hit. So don't stress too much. A lot of these things, critical point of water, Google will give it to you right away. Yes?
Is that log base 10?
I think it's log base 10, but I actually don't know because I never actually used this equation. I just put this equation up here to trash talk people's description of the eccentric factor. It's not the spherical nature of it. It's just a fudge parameter. I've read the original paper where they present the eccentric factor, and it's just argon is 1. Somebody had observed that. It was neat. Okay. Real equation of state seems big and complicated. Okay. This is a non-linear equation. Should we be scared by non-linear equations? No. We've already talked about how to solve a non-linear equation using Excel. Right? Use goal-seek. Now, in the case of a polynomial nonlinear, there's going to be multiple roots. So your initial guess has to be sort of trying to converge to the right root. Okay, so remember, not scary. One equation, one unknown. Just use a computer. Just use a computer. Yes?
Kind of related to this, but all the equations more so. So on the board, you kind of just circled kind of just a vague area.
Well, there's not a good answer.
How do we know when to use each one of these?
So, for the purposes of your sanity, compressibility factor is going to be the easiest. Right? It's going to be the least accurate, but by far the easiest. Virial equation of state, in my personal life, I would never use it. But it's a little bit easier than the cubic equations of state. In my personal use, I would always use the Penn-Robinson equation of state. But I've solved a lot of cubic polynomials, so it's not particularly scary for me, right? Because you can use this equation of state to develop steam tables. And in my graduate thermodynamics class, I make my students create steam tables using just the Penn-Robinson and the van der Waals equation of state, right? So for me, I would use this one. Compressibility factor, easiest, least accurate. Virial equation of state, kind of better, but really not worth the effort. If you're going to bust out the computer, you might as well just use one of these big baddies right here, right? Now, in the real world, always, 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 always the Penn-Robinson or a more advanced equation of state. okay? Because the compressibility factor will not work in a process optimization scheme because you want the computer, right, to iteratively solve these things. So this is an explicit or implicit equation, right? One equation, one unknown. Yes, it looks complicated, okay? But the computer can solve this no problem. Now let's just talk a little bit about the van der Waals equation of state. So it looks, and this is the Nobel Prize winning equation, right? I believe 1870, Nobel Prize winning, right here. P equals RT over V. Well, that's just the ideal gas law, right? But they added this minus B, and then they added this minus A over V squared. Anyone want to venture a guess what the B and the A signify? Okay.
The size, like the fact that particles aren't infinitely small.
Yes, that is which one, A or B?
A.
It is B, right? Because think about it. Let's say we only consider that molecules have size, right? This would be the right correction to the ideal gas law, right? The volume that's available for the molecule to move around in is being reduced by how much volume the other molecules are occupying. Okay, so V, let's say that V is in units of meters cubed per mole. What should the units of B be? Meters cubed per mole. It's the volume occupied by the actual particles themselves. A bigger molecule has a bigger B. Now, what is A? Now, let's suss out A. So A is a negative. So if A is positive, that would lower the pressure of the system. If A is negative, it would increase the pressure of the system. So let's just think about a box, right, with gas particles in it. So what does A correspond to?
Would be interactions.
It's the interactions. And the interactions become more significant as the volume gets smaller, right? So as V goes down, right, this is the volume occupied by the molecules, right? So as the container shrinks, there's more molecules close to one another. This term gets bigger, right? So that means it has a greater influence on the pressure of the system because then the molecules know that their friends are there or their enemies, right? Depending on what the molecules think about their friends. Now these A and B terms, again, related to the critical point. Right? So the critical point is a very important term. Now let's go to the Peng-Robinson equation of state. It's big and scary. But again, if I'm doing this in MATLAB or Python or Excel, do you know what I'm going to do? I'm going to write critical temperature, critical pressure at the top of my spreadsheet. Then the first thing I'm going to calculate, and eccentric factor, okay? Then I'm going to calculate this kappa. Well, that's an easy equation, right? It's just this number times the eccentric factor minus this number times the eccentric factor squared. I don't think we should be scared of that, okay? Then what do I do next? Well, then I can calculate A and B. Well, that's just a number times the gas constant and the critical properties. This is just a number times the critical properties. So I just have to make sure I get the units right. If you always stick to SI, you'll be fine. Pascals, cubic meters, kelvins, you're in the clear, okay? Well, now then I can calculate alpha. Well, because it's just this kappa thing that I already calculated in the line before, and then the reduced temperature. Well, that's just the temperature divided by the critical temperature. No big deal. Then I have this big scary equation, okay? R fixed. Temperature may or may not be fixed, but in this case, let's assume it is fixed. A times alpha. Okay, we already calculated A. We already calculated alpha. V, we don't know V. We know B. We don't know B. We know B. We know B. So the only unknown in this equation is the specific volume. So if I'm given the pressure and temperature, it's still just one equation, one unknown. Yes, it looks big and scary, but we have tools. We have goal-seek, right? Now you can also use a cubic root polynomial solver, right? The roots function in Python or roots function in MATLAB. Okay, then I'm going to go to the compressibility factor. So the compressibility factor, right? Z is a function of the reduced pressure and the reduced temperature. So I have a chart of reduced pressures and reduced temperatures, and then I read off the compressibility. Now the reduced temperatures are a bunch of curvy lines. Right? It also has the reduced specific volumes as well. So if you wanted to use P and V or T and V, this chart will work just fine. So let's say I'm at a reduced pressure of 0.5. That means I'm drawing a vertical line. I just need to find the intersection of two lines, and I've locked in all the properties of the system. So let's say a reduced pressure of 0.5, and I'll draw it up to a reduced temperature of, let's say, 0.95. I get my compressibility factor is about 0.77 or so. Right? Then I would take that, 0.77 is equal to PV over RT, and I can solve for whichever of these unknowns I want to. Right, so the compressibility factor, really quick and easy, but the least accurate of all of them. Okay. Don't be scared by the equations. Use the computer. If you know how to solve one nonlinear equation, you can solve all nonlinear equations. The only downside is that you have multiple roots, right? So one of those roots in the van der Waals equation of state is the density of the liquid. Right? You get the density of the vapor, the density of the liquid, and then a density in the middle that doesn't actually mean anything. Okay. Oh, hello. Now, I've got some videos here talking about, this one's the supercritical CO2. So I have the critical point of CO2. It is 31 degrees C and 73 atmospheres. So what's nice about it is that means you can pretty easily do it in the lab or in the classroom. So right now, looking at this supercritical CO2, we have CO2 vapor and CO2 liquid. At atmospheric pressure, CO2 doesn't boil, it sublimates. It's actually below its triple point. So it goes directly from a solid to a vapor, hence dry ice. Doesn't make any liquid CO2, it just makes CO2 vapor. Right? So that's why CO2 is all the way down here, and that's just based on where its critical point is. So what they're doing in this video is they've pressurized it to around the critical pressure, so about 70 atmospheres, and they're just gently heating it up. When things boil, and actually, I forgot to load my video. I have a video of boiling water, and I like to highlight the difference. So boiling water is a different type of phase transition. It's nucleation and growth. It forms a little bubble, and that bubble grows and it boils out. But imagine boiling water in your minds, okay? This is different than boiling water, okay? This is the supercritical transition. You'll notice there's no bubbles forming, okay? Now, as you watch this, you'll see that this liquid should get lighter and lighter in color, and this vapor will get darker and darker because the vapor gets more dense, the liquid gets less dense, and eventually their properties meet. And this is what we mean by the supercritical fluid. So I'll let it go, and we can see, but notice there's no boiling going on, right? They're heating this, but it's not boiling. Eventually, it just gets fuzzy, the interface gets fuzzy, and the whole thing disappears. And you can see there, see how fuzzy it gets and just kind of disappears away. So this is supercritical CO2. So the critical point is the point, the temperature and pressure space at which the vapor and the liquid properties become the same. And above the critical point, you can no longer have a vapor-liquid fluid transition, okay? So I'll be honest, it took me a long time to sort of understand what the critical point was, and I always wish that someone had showed me a video of it. Okay, the last one here is the triple point. This is just a fun one. The triple point is this point right here, where the solid, liquid, and vapor all coexist together. So you have freezing, melting, boiling, condensing, sublimation, all occurring simultaneously. So this fluid here is T-butyl alcohol. So right, a T-butyl group plus an OH on it. Its triple point is 21 degrees C and 5.6 kilopascals. So about 5% atmospheric pressure. So what they do is they boil it, and that cools it down, because boiling cools stuff down, because you have to give energy to those vapor molecules. Then they gently heat it up to warm it to that triple point. And again, this is a fluid that has a triple point that's convenient to do in a classroom. So eventually, Now it's freezing. And boiling. Right, so you have solid, liquid, and vapor all together. So you have to keep it right at this one point, otherwise it could all freeze, it could all vaporize, or it could all turn into a liquid. Right, but that's an example of the triple point. But all fluids have a triple point. Water has a triple point. It's just not in as convenient of a location. Water has a critical point, but it's like really hot and really high pressure, so it's not something we're going to set up in the lab or set up right here, right? But for CO2, you can do it quite readily. Okay, so that is my discussion of calculating densities. Yeah, practice exam on Friday. Sorry for the folks on the video, you didn't get to see this, but please come to class. All right, take care.